Good day to you. This is Galactic on a Friday in the first week of March 2026. Over here, you'll see a geometric figure that we have been using to illustrate some basic ideas in geometry. Now, I do a lot of preliminary workup to a subject which has been accomplished. I've produced over 1,500 video lectures in just short of 4 years, and this was for several purposes, but currently in the cutting edges of science, we have some amazing new prospects ahead due to the reinvention of the wheel, essentially. So I'll be going over a major discovery which I made about 4 years ago at the basic level of mathematics, numbers, and geometry. When I made this discovery, which is essentially the parameterization of the plane using circles, when I found out that this could be done, I tried to find out if anybody had ever done this or tried to do this. And what I'll be explaining right now, today, in this video presentation, which is mostly a lecture, as opposed to having a lot of diagrams, I will be going through the very basic sequence, but this will be comprehensive. It is high time that I made a video series that covers everything that I've discovered such that it can be assimilated in one view. One of the challenges in doing that I've discovered is that for the past 4 years, the essential insight that I made, that I discovered, as I claim to have discovered something, it has far-reaching consequences, which of course is good. And there's nothing wrong, and so it's strange to say that sometimes too much of a good thing can be overwhelming. I have made inroads into major questions in physics at two scales, that is, going out and going in. To the quantum level is where going in rather ends in a strange way, and going out, which of course we then have to deal with spatial infinity, which is quite a paradox. And then there are other paradoxes that arise along the way that are associated with our number system. And I will be covering the salient features of our number system in this video lecture, this video presentation. For now, I'm just going to turn off what you see over there, but this intends to be a warm-up or a prototype for a formal lecture series, which I will attempt to make into a single presentation that has a known outline. So this will be my first attempt at doing so. What we will cover are just some very, very basic notions that occur in mathematics and geometry, much of which perforce is going to be well known to you already. But I have already produced several video series in attempting to do just what I just described. And this will be significantly different because my approach, perforce, for 4 years has had to be roundabout for several pressing reasons, that my research has accelerated, that I make discoveries every day. And this even goes to sleep time, which is a phenomenon commonly reported among scientists and mathematicians in particular, that when you are working so intensely on a puzzle, a problem, a prospect ahead of you, which of course you're trying to solve, more and more parts of your mind tend to come into play. And this is, of course, rather, I would just say, spooky for now. We are probing all of these phenomena of the human mind. But the human mind is quite powerful, and it is adaptable within its scope. So you may not realize just how much power your mind has. But it is interesting in this connection of making these video series that I've discovered rather a new source of, I guess you would say, power or insight, or just better and better success, more in efficiency from having made these presentations, which of course I listen to myself. And this may sound strange, but it may not, but it's very commonly reported that when you are concentrating on a subject for so long, you start to notice thresholds which really only appear in retrospect. That is, it's hard to notice while things are changing. That you're just doing your practice as every day. You follow your same routine. For instance, for we have some rather noisy planes fly over sometimes. I apologize for that. That's not that common, but I had to pause for that one. That was a low flying plane. But my attempt today will be to give a comprehensive single shot lecture that covers the entire sequence of what I've discovered. But I'm going to concentrate on the basics because it's the basics that reveal the structure that's necessary to essentially to use a new kind of geometry, which I must say is a rather challenging thing to say. It still sounds so even to me. Because of course we expect that we have been told everything in our educational system. This is a somewhat naive assumption, and perhaps you don't share it, or perhaps you can at least sympathize that some people may feel that their education system must have given them everything worth knowing on certain topics. And of course, this would have a context, and it may not be perfectly true, except in some restricted sense. But we believe that we haven't been denied any information that may be critical. We always expect that there are new discoveries that were perhaps just sitting right under our nose, and it just nobody ever put the pieces together to notice something valuable, some useful bit of knowledge. So when we're talking about structure, we're talking about the same topical area as geometry. Geometry, I think it's fair to say, is devoted to structure, but it is, of course, a specific kind of structure. And in geometry, the key word is abstract, which raises some philosophical issues which are well worth exploring, not right now, but are numbers real? Really, are even the geometric figures that we can draw and see, are those real? That's quite a delicate question because how would you prove one way or the other that they're real? Well, usually what happens in these kind of inquests, this kind of probing, which of course is quite natural, but some questions can be so challenging that you literally are not sure how to get a grip on the problem. Like reality, what is real? What is usually meant is, do numbers have such a legitimate function that their function can be stated such that it can be proved? And I don't see any objection using that simple definition to say that numbers are real. What is most often the confusing aspect is by not is when it's not made clear precisely what you mean by real as opposed to another kind of real, because physical real generally implies matter. But that also leads in a philosophical direction. Is energy real? I think everybody would say it is real, but it's not. I'll just state point blank, energy is not real in the same way that matter is. And this goes all the way down to the definition of the proton, which is essentially the building block of matter. but the electron is the building block of energy. And that's also very interesting, because what then of the photon, which in a certain sense you would define the same way as an electron, but they have two quite different characteristics. That the photon is not as particle-like as an electron. So this gets to the wave-particle duality, so that exhausts our top-level abstract view of what we're addressing when we address geometry. It is real, and the reason it's real, as a mnemonic, as a way to convince yourself on a moment's notice if geometry is actually real or not. It's not that it's physically real, because of course it's not, to the same degree as numbers are not real, because they're not physical, they're abstractions. But then when you just pair off the notion of physical reality, which of course is quite specific, something is there's a footnote to all these things at the quantum level, but physical reality is physical. It can be measured. And we get into some interesting definitions of measurement then when we get to the extremely tiny. But all of this can be summed up very neatly by pointing out that structure is real. A building has a structure because there were architects and engineers who had a blueprint for the building. So the building is not just made of material. The material is real, it is physically real. Is the structure real even though it's not physically real? It's an abstraction of the human mind. You know it's there, but does that make it real? That is a philosophical kind of a trick question. The correct answer in context is, of course, it's real. Structure is real. It's part of the storehouse of knowledge that we accumulate. It's not just data information, it's also structural relational information. And this word relational will be a key notion, a key concept in my particular approach to numbers and geometric objects. Now, in that diagram that I just showed you over here, it was simply a circle. That's to trigger part of the brain, is how I explain that briefly. We do have a geometric part of the mind that is aware of these abstractions and can use abstract objects such as the straight line or the circle quite conveniently. So now we can jump into the sequence that I want to present to you, which I've never done as fully or as concisely as I intend to do now. So there will be some baseline of what I say that I've discovered, which is quite a long list now, but it just begins with a couple of basic insights into structure. So let's begin with Euclid. This will be a high-level view of Euclidean geometry and the course of science up until now, so that it is not tedious, but I do wish to get across a certain gradient and introduce a couple of key terms which will guide us through the rest of this sequence, which, let me inform you at the outset of what you are about to hear, that what you can expect to be hearing as I give this presentation is a complete outline and description of a kind of geometry, which I don't want to try to define right now, because that is the purpose of this sequence, is to actually lay it out. Not try to summarize it, but actually show you what it is. All right. The way that numbers were developed for use by humans can be traced back more or less to its sources, which gets into the very, very tricky area of ancient history. However, we can say to certain thresholds of calendar time just about how long ago, and in other words, when and where. When and where were numbers conceived by the human mind? That question has levels and it goes deep, where you might try to recapitulate the structure of numbers because there are different kinds of numbers. But essentially, numbers were well known by the time of Euclid. A lot can be said about the history of numbers themselves, but our first grade concept of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The first 10 counting numbers are those numbers. And then it goes on from there. Those numbers have been known since time immemorial, the counters. So that is the basic definition of a number, because the simplest application for a number system would be to count things, such as apples. To jump quite a few centuries past Euclid, we simply will point out that what Euclid gave to the world was not numbers, but it has an extremely important relationship to the development of numbers. We have structure and we have measurements. Measurements are usually construed as something that you make on a structure. So that if you have, for instance, a rectangle, you would call that a structure, but it has nothing to do with numbers. But if you talk with the Greek geometers or any modern geometrician or geometry, though those two words are both used for someone who does geometry, numbers are always implied. And the reason why is that they go together so perfectly. So we have two separate concepts, one of which is structure, and we give the branch science named geometry to the study of structure in that respect. Mathematics, of course, refers not to structure. That's not the primary definition of mathematics, for the very same reason that the primary definition of geometry is not numbers. The primary definition of numbers is not geometric. But then it turns out that by the 20th century, once the number system was fully ramified over centuries of development, where first, I believe it was the negative numbers that were discovered, and then zero was discovered. And that might surprise you that Euclid had no concept of negative numbers. It wasn't a concept that anybody had. Although it was developed in India, they did have a concept of zero. Negative numbers, which seems so logical to us now, because very early in school, we're taught the number line. And the number line is quite an interesting term because it turns out that you can prove that the numbers, beginning with the counting numbers, but really going all the way to fractions, which is a different form of number using two numbers with that little line, which may or may not have a name. But a fraction is a two-component number. That is true, but you may never have heard anybody say that. But it should make common sense to you that when you write a fraction, you have to write two numbers. And you cannot write zero in the denominator. And it's rarely seen because it's equally, well, not equally, but it's a mistake to put a zero into a fraction because zero has a very specific relationship to the other numbers that differs under addition or multiplication as it's put by the mathematic theoreticians. They would say that there are two spaces in which numbers operate. and one of them is linear space, which uses add. And that makes sense to you and me once you hear it, but I rarely hear it put that way. That the reason that we have a number line is that numbers are linear. That is, all numbers imply a line. You can't have a number without there being a line, because a number by itself has no meaning. Unless you just use it as a counter. In other words, you say that there are 42 apples. Well, that's not a structure. What makes it so interesting is that it always works the same way. If you say that there are 4 objects, and then you clear the table and put out 4 more objects, but they're different objects, there's still 4 of them. And that's totally unambiguous. And so that's the basic meaning of a number, is a counter. But in the case of distance, distance is what Euclid was computing in his book Elements. The most famous book ever published by man is Elements. And it was famous for over 2,000 years and still is. Well, what was Euclid's secret that made what he put into that book so incredibly important? Well, there are several there are several ways you could answer that, because Euclid accomplished more than one really groundbreaking accomplishment. But one of them was to introduce a geometric concept of distance. He didn't introduce it, but he introduced it in a systematic way that has become the paradigm for all scientific axiomatization sequences, which is quite an important step in science, is to axiomatize your system so that you know what you're talking about, so that you can communicate it. And science is communication, of course. The discoveries made by Euclid, which he documents in his rather long book, Elements, begins with deceptively simple statements. And when I say deceptively, it's actually quite profound. It's not deceptive like he's fooling you. It's deceptive that you don't realize at first just how strong are the statements that Euclid makes to axiomatize planar geometry. Planar geometry. When you say planar, you're referring to the blackboard. If you're dealing with spheres, you would have to put the spheres into a space in which they fit. And there are different ways of labeling what kind of space that is. The most common label you hear for volume space is 3D. And we're going to find out in a moment that that is simply one way to create a space. And that is Euclidean space. When you say 3D, we all know what the 3 means. It begins with a line. It goes to a second line, which now exists in a different space. The line could be said to exist in a space, but it's rather arbitrary what you would call that. But what you can say, and what you should say, and what has been said, in fact, is that the line exists in a space indeed, in the same way that a sphere exists in a space, but they're not the same space, because the space itself has a different implicit structure. And a couple of examples will make that clear. When you're talking about just space as space in a room, that's called volume space. And when it is named with a Euclidean parameterization, which we'll cover what that word means, you may already know, but all it means is that you're trying to define a space. And when you parameterize the space, you're adding numbers to it. So when you draw a line, you have to draw it in a space. And it is commonly conceded, in fact, the only way this is ever stated is that when you do draw a line, you're drawing it on a plane. So the line is a planar figure. The line is not ordinarily construed as existing in volume space. But then again, there is nothing really wrong with saying that, because the line would in this relationship be called a subspace of the plane, but the plane itself is a subspace of volume space, because you just take the cubified space and squish it, and you have a square. If you squish it again, you have a line. A line is 1D. If you expand it orthogonally, you get a 2D plane that's been linearized. And if you expand it again such that it's cubic, you get cubified volume space. And that's 1D, 2D, and 3D. Now we will be getting into 4D momentarily, and that may be a subject which either interests you or confounds you or somewhere in between. I can assure you you're not alone, because in 4D, one of the ortho lines is imaginary. So that covers the four main linear dimensions, beginning with the line, which is a planar figure. All right, so Euclid introduced us to the line and linear systematic space, which refers to 1, 2, and 3D. It's very interesting that he did not begin his book Elements by defining the line. He needed exactly one sentence before he defined the line, which he defined in sentence 2. But in the opening sentence to his immortal book, he defined a point. And a point, today appropriately called a Euclidean point, is 0D. And that's an interesting use of the number 0. And 0 is already a peculiar number. So when you say 0D, the only way you can really do that logically is by already having defined a line. Because a point can't just exist because it literally isn't there. If you have a line, you at least have something, because you can define, certainly in the geometric portion of your brain, that there is such a thing as a line. But there's really no way to objectify a point in the same way that a line can be objectified because it can be seen. But a point cannot be seen. And it's defined that way. 0D, the way Euclid defined it, he defined 0D. He did not use the number 0, though. It had not even been invented or conceived in the mind of man. It was quite a shock when it was suggested among the Europeans into the modern age, but quite a long time ago. 0 was conceived as a specific number that is the absence of quantity. It's a placeholder. And that's really how the 0 as a cipher was first used by the people of India. The mathematicians of India developed a cipher as a placeholder in a what you would call a digital system. So numbers have been developed in several ways, both notationally and conceptually, over a period of many centuries. Today, we're rather comfortable with the concept of a number, but we are also aware, depending on your level of education, but we are all aware that mathematicians have some really peculiar problems having to do with the numbers that have been invented for obviously good reason. In other words, there are pitfalls, such as 0, but one of the pitfalls of the linear numbers that the Pythagoreans are accredited with if not having discovered, certainly having reacted to the existence of irrational numbers. And irrational numbers have a certain relationship with zero, because zero has a kind of irrationality. What irrationality means is worth defining, so we'll do so quickly. It's obviously the opposite of rational. So what does it mean to be rational? Mathematically, it means you have two quantities in relationship. So if you have a relationship between 3 and 2, you can do computation to get relationships that may exist between those two numbers. If you want to know how much bigger one number is than the other, you can use subtraction, which is simply another version of addition if you allow the addition of negative numbers. And you may already know that, otherwise it may sound like a riddle. It's not greatly significant, but I do want to mention these things in passing, that when you're computing distance, you're using add, but you're using it for a countable unit that is not a thing. It's rather a slice of space. And it's an abstract slice of space called a linear distance. So that if you have two objects, you can literally take a tape measure or some way of measuring the distance between the two objects, and that will be its linear spatial separation in metric units. And the metric units are what we call numbers, because we're using the counting numbers to develop the idea of a measurable. And a measurable it's a term that has come into vogue in quantum mechanics. It means what it says, essentially. It's something that you could measure. What can you measure? Well, the first thing that men learned to measure, you could also go into weights. There are ways of weighing things. That's a measurement. But distance, that's what we wanted to measure. That's what Euclid dealt with, was linear spatial separation, for which we use the counting numbers to make a metric on the object, which is a line. And the way you manipulate the numbers on the line is by using an operator, and that's called add. You don't need subtraction, and I'm just going to leave it at that without proof, but for homework you can verify to yourself. There is no such thing as subtraction except by a convenience. You don't need it. It's not logically necessary. So we only have one operator for the line. It's called add. And now for distance, there is no such thing as negative numbers, because there's no such thing as negative distance. Because distance, the separation between what Euclid would say is 2 points, generally 2 points on two objects. You're measuring the distance between two objects by drawing a straight line between two objects that connect the 2 points at the surface of those objects. So then you can metricize that quantity. That's a quantity of distance. And you have to now unitize it so you can compare measurements. Because if this is a measurement of 10, this measurement over here will be 12. And those are numbers that have a relationship that is well defined, it's coherent and complete. So now you have a metric for your space. And what is the space again? It's the plane, because the object is the line, and the line is a planar object. Because the next higher space, going hierarchically outward, would be from a line to a linear plane. It has to be a linear plane if you're parameterizing the plane with the line, which we've done. So it takes two numbers to parameterize the plane, and that's a lot in a nutshell. So I hope you're comfortable with what I just said. It's not difficult. It's just so basic these kind of explanations tend to get overlooked in favor of other explanations, which may show bias, but it's not really important to us now. What is important to me in presenting this to you is that you get this the right way, so that everything makes sense no matter what comes at us, and a lot's going to come at us in a moment. But the very basic definition of Euclidean geometry is that it begins with the plane, and the approach to the plane is to deal with the plane with lines. And that is generally the definition of geometry. Although, as I will be showing you now, that is an incorrect definition of geometry. Why? If you're very clever or you've been tuning in, you may be able to guess or deduce what is the huge problem with the linear number system. It's actually overwhelming when you face it squarely. So let me just let the cat out of the bag. The distinct drawback of the otherwise amazing linear number system, this is not a critique of the linear numbers. It is an expose of how they were discovered and in what context do they exist, so that we know everything we want to know about how this was accomplished. How did we get our modern number system? How did we get, for instance, the Einstein field equation, which is a 4D equation, which can be understood, but you do have to understand what is meant by 4D. To do that, we go right back to Euclid, who started with 0D to define a point, because he had reasoned out that in order to define what he wished, which was a line, he had to define the point first, because he found it necessary to define the line as a collection of points, what would be called a set of points today. But he wasn't quite that sophisticated to have come up with a notion of a set, at least not explicitly. Now, from this simple and humble beginning, but also rather profound, we would have to say now, we find out that Western science, really, you could just say science and leave out the West and East. It's not really relevant here. But it just accept in the way it developed historically. It was India, if you consider that to be the West, which I'm not sure everybody would, but certainly the Greeks are well known for having developed linear geometry, which is what? Structure. They were not interested in numbers. And I'm going to leave it at that without any argument, because that is simply true. They were interested in quantities, but the way they thought of a squared number was as a square. When we're taught a squared number like x squared plus y squared equals the hypotenuse squared, we just think of that as a little subscript 2 that has a geometric meaning, probably. That's true, it does. But the Greeks did not think that way. When they saw the x quantity, a linear quantity, they literally made a square out of it and drew it. And then for the y-axis, you take that distance and you square it by making a square out of it. So now you have this right triangle with two squares sticking out orthogonally. And what they figured out is that if you combine those two areas, that it makes the area of the hypotenuse. So they weren't talking about numbers. They were talking about visible quantities. Now, the way you and I were taught, I will just say this and leave it at that. We don't want to get into philosophical distinctions. It's not necessary here. But leave a comment if you would like me to change direction or change my tone in some way, because I'm leaving out a lot. And that's necessary in a quick summary. It's a trade-off and it's quite an art, but I've been practicing for a while. Let's continue with the main insight, which is that Euclid, really the Greek geometers, gave to the world linear geometry, which is structure. What came after that was a combination of advancements in structural manipulations, such as symmetries, such as relationships between angles. This all came about as the manipulation of actual, you could say, planar physical quantities. An area is an actual structure. It's not a number, it's an actual presence. Visible, it's a visible thing as a square. So when you add the two sides as their squares, you get another square, which is really saying something. It's not very common that when you put two numbers, one on the y-axis and one on the x-axis, to make an arbitrary right angle, that those two numbers will add to a perfect square. One of the examples of that is the square of 3, which could be x, and the square of 4, which could be y. So a 3 by 4 right triangle, you add the two squares, which would be 9 plus 16, that's 25, which is a perfect square. Those are called Pythagorean triples. But alas for the Greeks, what they found out, and without going into the whole story, which is extraordinarily fascinating, they found out about irrational numbers. That is, the two quantities on the x and the y aspects could no longer be combined into an actual quantity. And you might want to ask yourself, what did the Greeks think about an actual quantity? Because in the calculus, you can get a number as precise as you like. But by saying that, you're making a tremendous admission, is that the number that you're after cannot be had. You will never get that number. On a perfect square, you can take the hypotenuse of a right triangle whose sides are each 1. You just draw a diagonal across the square, and that will be the hypotenuse of the x and y quantities, which adds up to 2, and so now you must take the square root of 2, and that's where you fail. Now, what we're going to do now is extend the concept of the irrational number, which is traumatizing. It destroys the system to a certain respect, that is, to a certain threshold of precision, which of course is to be preferred, is precision. But when you're dealing with the irrational numbers, it's no longer precise. So if you can't get that number, you actually cannot say that you have a quantity. You have a quantity that's close to something, but it can never be precise. So that's a very strange aspect of the square root of 2. Now, when the Greeks approached the circle, you can immediately see that there will be some problems in computing a circle. And you're well acquainted with those problems, which essentially comes down to pi, which is an irrational number of the same type as the square root of 2. It's interesting if you would like to do a study of your own, which I recommend, but I can't go into now, the definition of a transcendental irrational. A transcendental number is a specific kind of irrational number. And there's different levels of irrationality, which again, I can't go into now because that's not our main topic. But this goes deep, fast, really fast. But when you just look at what caused this enormous problem with numbers, forcing us to such strange tools as the calculus, it's because of the presence in the linear number system of irrational numbers. So that's the definition of irrational. It's the opposite of rational. Well, what is rational? Rational is when one of the numbers is 3, the other number is 4, and therefore you can compute 5 on the hypotenuse. That's rational. So what specifically does rational mean? It means that you have two quantities that are related. You can rationalize them. That means you can make a fraction out of them. That two numbers have a ratio. Ratio is the root word of rational. And that's the comparison. It's a comparison between two quantities where you want the relationship to be exact, not the calculus. It has to be exact. That's what you're forced to, is the Pythagorean theorem. If you want to be able to compute distance on a plane, if you have just two lines, you can only measure distance on the x-axis or on the y-axis. But what you want is to measure a distance from the origin to anywhere in the plane. And most of the time, that's going to be on an angle, that is, on a diagonal, not on one of the orthoaxes, each of which has a number system attached. So when you get a distance from 0 to the point 34, the distance will be 5. But if you try to get the distance from 0 to the point 11, the distance is the square root of 2. And that simply cannot be computed, which has been argued so heatedly that I swear there have been countless times where two scientists, two mathematicians, two geometers, not geometers, but mathematicians generally do this. They will go to blows. They will go to a duel. They'll want to kill each other over this. Well, we don't want to get involved in that kind of emotional conflict, but this goes right to the nerve, right to the meat, because there are so many mathematicians who base their entire pride system. They base their whole identity, and many of them base their livelihood on the truth of linear numbers. And these kinds of mathematicians, of which there is a legion now, they do not like to have anybody like some profane asshole like me come along and put my stinky, filthy, dirty fingers on their sacred cow's asshole. They don't like their goddamned golden cow being slighted or touched. You leave that fucking cow alone. That's linear algebra, on which thousands of books have been written. What I'll be showing you now is that the linear number system is saddled with insurmountable problems that have caught up with science, such that it is the mathematical system itself that has destroyed science, ruined it, and science is dead. It's absolutely stone cold dead. There is no more progress. Not only is there no more progress being made, as of today, in the 21st century, there is no longer progress possible for one reason and only one reason that I discovered. I discovered the roadblock that's holding science back and has been for about 75 years. Science has been absolutely in a coma. And the reason is now absolutely certain. There is no question that I am right. And I will not allow any argumentation against my primary thesis If you want to argue with me, you first have to show to me that you understand what I'm saying. So I'm going to tell you now what it is that I'm saying, so that in the future, when you're rooting for me, when you're betting on me, when you love me and you want me to get the better of the situation in a debate, and you're on my side, you must at least know what I'm trying to say. So I'm going to tell you why you can believe in me and you cannot believe in anybody who disagrees with me. I'm right. So what am I saying that I am right about? All right. Once we had Euclid and we had linear geometry, which I just very carefully defined. So you know what I'm saying now. When I say linear geometry, I want to make something very clear right now, which will be a source of confusion to you if I don't make it clear to you now. So hold on to your seats for just a moment as I explain a delicate concept called componency. Componency. Numbers have a characteristic, all numbers do, of componency, and it is a counter number. The linear number system is a one component number system. Let me say that again and let this sink in because of what I'll say after it. The linear number system is a one component number system that uses add, which uses 0. So 0, add, and one componency are synonymous. Those mean the same thing. Linear, single componency, and the use of 0 as the Archimedean. And you know what that means. The Archimedean means the balance point of the line. It's the special spot on the object that makes a fulcrum. And Archimedes discovered this principle, that if you draw a line, you know what its value is? It's 0. Do you know why? Do you know why a line has a value of 0? It's because of valency. That if you go 1, 2, 3, 4, infinity, each one of those numbers has a plus in front of it. So even though it's a one component number, 1 is a one component number, so is 2, so is infinity. But it's plus infinity, and you have to write the plus. Any number has to have something in front of it to indicate its valence. And the fact that we don't do that, we leave the plus off, has caused an enormous amount of confusion in mathematics. I'll get to that eventually, but that would be an aside right here. So add is an operator, and there's only one other operator besides add, and it does not apply to the line because it doesn't apply to a single component number. And that operator is called proportionality. So this is going to cause you to lose your mind in the sense that what you were taught in grade school for about 8 years was absolutely incorrect. That you were not taught the operators correctly. First of all, you were taught that there's such an operator as subtraction. I have proved there is not. There is no such operator. There is only add, and that's the only operator that works in linear space. And so it's illegitimate for someone like Einstein to come along and start using multiplication because he doesn't know what he's doing and it caused an error. And all of Einstein's equations have errors in them, and so do Dirac's and Schrodinger's equations. All the equations of all the modern physicists are riddled with errors, and they're quite subtle. And they do tend to cancel. There are ways of canceling these enormous mathematical problems because you think that the line, which is an object in the plane, which can be parameterized with numbers, you can just disregard the fact that the line only uses add. Nobody was taught that. What I just said, which is true, is taught as a lie. That you have multiplication and division. You have 4 operators. That's a lie. There are only 2 operators. There are not 4 operators. And when you start using multiplication and division with single component linear numbers, you fuck yourself right up the ass. Completely. Right out the gate. You made an error. You made an error because you're applying multiplication and division to linear space. You cannot do that. It cannot be done, and I proved that. So everything we were taught about mathematics is absolutely ass backwards. There is no such number as 0 because you cannot make 0 a 2-component number. Let me ask you something. How do you parameterize the line? Well, you may not know what parameterize means, but I'll teach you what it means to parameterize, to metricize, and to quantize. And you must know the distinction between those 3 words. Parameterization, which is a 7-syllable word. Quantization and metricization. Metricization, parameterization, and quantization. These have to do with linear space, which is when you start with a plane and you draw a line. You cannot do that. That is an illegal operation. The plane does not have lines. It simply doesn't. What does it have? Circles. It has concentric circles. And those are 2-component parametric objects, such that a circle as a planar object cannot take a single component number parameterization because it's not linear separation. It's circular separation on concentricity, which is concentric circles. Well, there is a specific distance between each circle. And the distance between the circles is true distance. That's physical distance. All physical distance is circular distance because it's spherical. And that explains gravity and that explains light. In the next video, I will prove both those statements, and from that, we'll get the unified field solution. So you're about to witness history. I have made history, and you're going to be the first to see the greatest breakthrough in science of all time. I discovered it. It's very simple, but the way I will be presenting it to you, it will also be a challenge, so that you will have to think, because for the first time in your scientific life, you're actually going to have to turn on your brain. And this may be the greatest gift that I've ever given to the world, is I am going to force you to turn on your mind, probably for the first time. I've broken through the barrier. I made it. I made it out of this mess, and I can see back into where we live. I am going to get you out. You're going to see the number system and the geometry that the universe uses. Thank you.